All right, time to step away from the maths. Let's talk about putting electric fields to use. One thing you can do with them is to use them to steer charged objects, like charged drops of ink in an inkjet printer. The way it works is that tiny drops of ink pass through an electrode. When the electrode is on, it creates an electric field which charges the droplets by induction. Then they pass through the deflection plates that steer them down away from the paper into the gutter. When the electrode is turned off, the droplets aren't charged and don't get deflected, and so they go on to hit the paper. The computer delivers the on-off message to the electrode via the charging control. Let's do a very small calculation about the deflection of a charged ink drop caused by an electric field. This is a type of question popular in the HSC exam because it combines electrostatic force with the motion of a projectile from mechanics. So we're going to work out that for a charged ink drop coming horizontally, so in the x-axis direction, between the plates, what will be its vertical deflection by the time it reaches the end of the plate? Now the values are what you have shown there, and the working now I'll show you on the tablet. Now we're going to be looking at the problem of an ink drop that is going to pass between two parallel charged plates. So it's coming along here in the x direction, but when it reaches the plates there's an electric field between them, and so the drop is going to have a vertical deflection by a certain amount, and that's what we're going to have to calculate. So the things we know about the situation: the plates are 1.6 centimeters long. We have this drop going initially in the x direction at 18 meters per second, and we have a few other quantities here. So we know that the field strength is 1.4 by 10 to the 6 newtons per coulomb. We know that the charge on the drop is 1.5 by 10 to the minus 13 coulombs, and we also know that the mass of the ink drops is 1.3 by 10 to the minus 10 kilograms. So this works just like any projectile motion question. We have an object moving horizontally to begin with, but it's going to be going into a vertical field, and so there'll be a vertical force that is uniform, and so there'll be a vertical acceleration. Now for gravity problems, the acceleration is going to be 9.8 meters per second squared. Here we're going to have to work out what the acceleration is, and then we can apply it to all the usual projectile motion equations. So let's start with the electrostatic part to work out the force and the acceleration. Now the force is going to be the electric field times Q. So we have 1.4 by 10 to the 6 by 1.5 by 10 to the minus 13. That will give us a force of 2.1 by 10 to the 7 minus 7 newtons. Now we can use Newton's second law to work out the acceleration. 2.1 by 10 to the minus 7 over a mass of 1.3 by 10 to the minus 10. That gives us an acceleration of about 1.62 by 10 to the 3 meters per second squared. So we want to know what will be the vertical deflection once it's gone forward a distance 1.6 centimeters. So what we usually need to work out in these projectile motion problems is what time does this take. So we want to know the time to go forward 1.6 centimeters. So in the horizontal direction we have a constant speed and we know the distance. So the time is just going to be the distance over the speed. So 1.6 centimetres, which is 0.016 metres over 18 metres per second, it will be 8.89 by 10 to the minus 4 seconds. And then we need to know what will be the y distance in that time. So it will be uyt plus half ayt squared. Now initially there's no vertical speed, so that's just 0. Ay was, so here we've got our half, ay was 1.62 by 10 to the 3, and then our time 8.89 by 10 to the minus 4 squared, and we end up with a deflection of 6.4 by 10 to the minus 4 metres, or 0.64 millimetres by the time it reaches the end of the plates.